All right, welcome to the classroom. Today, let's have a look at the second half of C2L2, forces of friction. Friction may seem like always makes movement more difficult, but it always opposes motion. However, friction is actually essential for much of the motion that we rely on. Have you ever tried getting around on ice? The reason that walking, driving, or riding a bicycle on ice is difficult is the lack of friction. When you take a step, you push backward on the ground. The static friction of the ground opposes the attempted motion of your foot and exerts a simultaneous and opposite force that propels you forward. A sprinter, such as the one in Figure 1, tries to maximize the forward force of the ground. This means wearing shoes that have a large force of static friction with a running surface. It also means pushing on the ground with a force that has a large component parallel to the ground. However, if the sprinter pushes on the ground at an angle that is too shallow, his feet will overcome the static friction and leap on the track. So next, let's have a look at types of friction. There are two types of frictions, which are kinetic and static. So here, figure 2a shows a hockey puck sliding across the ice. Although the surface is quite slippery, there is still a small amount of friction. Eventually, the force of friction stops the puck. Figure 2b is a free body diagram of the hockey puck. The puck moves horizontally to the right. Only one force acts along the horizontal, the force of kinetic friction. The puck's velocity is to the right, so the force of friction opposes his motion to the left. Two forces act in the vertical direction, which are the weight of the puck or the force of gravity, and the normal force exerted by the ice surface acting on the puck. So first, let's have a look at kinetic friction. The force of gravity and normal force cancel each other in the y direction, and the puck's motion is entirely in the x direction. So why do you think you need to know about the forces along the y if they cancel each other? Actually, the normal force is closely connected to the force of friction. For a sliding object, the magnitudes of these two forces are related by this formula. Fk equals mu k times Fn. The number mu k is called the coefficient of kinetic friction, which is a number that relates the force of kinetic friction between two surfaces in contact with the normal force where they meet. The frictional force occurs when two surfaces are in motion or slipping with respect to each other. As the coefficient, mu k is a number without dimensions or units, and its value depends on the surface properties. For a hockey puck on ice, mu k is relatively small, so the frictional force is similarly small. The value of mu k depends on the smoothness of both the ice and the hockey puck, and might typically be 0.005. The coefficient of kinetic friction for two rough surfaces is larger. For example, the surface of wood is much rougher than the surface of ice, and the surface of wet snow is rougher than that of ice. For wood slipping on wet snow, the coefficient of kinetic friction is about 0.10. So here, table 1 lists some coefficients of kinetic and static friction. We'll Of course, we'll discuss static friction in next lecture slides. So these are the kinetic and static frictions for some common materials. These values of mu k shows that the frictional force depends on the properties of the surfaces that are in contact. Note that the coefficient of kinetic friction is less than or equal to the coefficient of static friction. Note also the value for synovial joints in humans. Biomedical research into friction in joints is an advancing field here. Also, remember that the magnitude of the frictional force depends on the normal force. If you increase the normal force, perhaps by adding a additional mass to the top of the hockey puck, the frictional force increases. However, this relationship is not a law of nature. It is simply an approximation that works well in a wide variety of cases. To derive a fundamental law of theory of friction, we need to consider in detail the atomic interactions that occur when two surfaces are in contact. This problem is quite complicated and is currently a topic of much research. Okay, so next, let's have a look at another type of friction, which is static friction. So the example of the sliding hockey puck illustrates surfaces that are moving or slipping against each other. But what about when two surfaces are in contact but not slipping? Such cases involve static friction. So here, as you can see in figure 3a, a worker is trying to push a refrigerator, but the refrigerator is not moving. This example demonstrates static friction. Unlike the hockey puck example, here the person pushing on the refrigerator adds an additional force. The FBD in figure 3b shows the additional force of the pushing push working against the force of static friction. Intuitively, we know that when the force exerted by a person is small, the refrigerator will not move, right? Since the acceleration is then zero, the force of static friction and the force of push cancel each other. Then we have the following relationship. MA equals the net force along the x-axis. Well, MA equals 0, then FA should equal FS, right? The force of static friction is sufficiently strong that no relative motion or slipping occurs. In terms of magnitudes, we have the magnitude of FA, which is the applied force, equals magnitude of Fs, which is a static friction. However, the value of the applied force, Fa, can vary, and the refrigerator will still remain at rest. That is, the worker can push harder a little or not at all without the refrigerator moving. In all these cases, the frictional force exactly cancels Fa. The only way this can happen is when the magnitude of the frictional force varies depending on the value of Fa, described by the magnitude of the applied force Ma is smaller than or equal to mu s times Fn, where mu s is a coefficient of static friction. The coefficient of static friction is the number that relates the force of static friction between two surfaces to the normal force when they meet. The term static means that two surfaces, the floor and the bottom of the refrigerator, are not moving relative to each other. the magnitude of the force of static friction can take any value up to a maximum of mu s times Fn. If Fa in figure 3 is small, the force of static friction is small and will cancel Fa so that the total horizontal force is 0. If Fa is increased, the force of static friction increases, but again cancels Fa. However, the magnitude of the force of static friction has an upper limit of mu s Fn. If Fa is greater than this upper limit, the walker will succeed in moving the refrigerator. So here, let's revisit the concept of coefficient of static friction. So the coefficient of static friction, mu s, is actually the ratio of the maximum force of static friction to the normal force. So you need to be careful with the concept here. Mu s means a ratio of the maximum force of static friction to the normal force, okay? That's a little different than the coefficient of kinetic friction. All right, so next let's have a look at a tutorial which explore friction problems and calculate acceleration, angle, and mass. Okay, first, tutorial 1, solving friction problems. So let's have a look at sample problem 1, comparing pushing and pulling. A walker must move a crate that can be either pushed or pulled, as shown here in figure 4. The walker can exert a force of 3.6 times 10 raised to the power of 2 newtons. The crate has a mass of 45 kilograms. The walker can push or pull the crate at an angle of 25 degrees. And the coefficient of kinetic friction between the floor and crate is 0.36. The walker wants to move the crate as quickly as possible, but he does not know whether it is better to push or pull. So there are 3 questions. A, calculate the acceleration when pushing the crate. B, calculate the acceleration when pulling the crate. C, evaluate your answers to A and B. Does it matter whether the walker pushes or pulls the crate? Explain your answer. Okay, here I'll give you 10 minutes to have a look at this question by yourself, and then we'll have a look at together, okay? You can start now. Right, let's have a look at the solution together. Okay, first question A. We're given the following information. The magnitude of F equals 3.6 times 10 to the power of 2 newtons. And the mass of the crate is 45 kilograms. Theta equals 25 degrees and mu k equals 0.3036, right? So we need to find the acceleration when pushing on the crate, A1. So we can draw a FBD for the push. The force in the y direction must be 0 because the crate is not accelerating upward or downward. Calculate the normal force on the crate as well as y coordinate of all the forces on the crate. The walker is pushing, so make the y component downward. Use the horizontal components to calculate the acceleration. Therefore, we have following relationship. The net force along the y-axis equals Fn minus Fg minus Fa times sine theta. And this gives us normal force Fn equals Fg plus F8 sine theta. Put all the values in, we have the normal force is about 593.1 newtons. And the net force on the x-axis is F cosine theta minus mu k Fn. Again, put all the numbers in, we have the net force along the x-axis is about 112.8 newtons. Therefore, the acceleration A1 equals net force along the x-axis over the mass of the crate, which is about 2.5 meters per square second. So in question 1, when you push the crate, the acceleration is 2.5 meters per square second. Okay, next let's have a look at question B. So the method is quite similar, right? So in this case, the x component of the force is the same, but the walker is now pulling. So the y component of the walker's force changes. It is now upward instead of downward. So we can again draw FBD for the pull. Net force along the y-axis equals Fn minus Fg plus Fa sine theta. This gives us the normal force, Fn, is around 288.9 newtons. And the net force along the x-axis is Fa cosine theta minus mu k Fn. And again, put all the numbers in. We have net force in the x-axis is 222.3 newtons. So we can find corresponding acceleration by using the net force along the x-axis over the mass of the crate, which is 4.9 meters per square second. Therefore, we know the acceleration when pulling the crate is 4.9 meters per square second. So if you compare these two numbers, it's easier to find the answer for question C, right? So the walker should pull the crate because pulling decreases normal force on the crate. Consequently, the force of friction is less, which produces a greater acceleration. Okay, any questions? All right, if no questions, let's consider another problem. Now let's consider this problem here. A crate is placed on an inclined board, as shown here in figure 5. One end of the board is hinged so that the angle theta is adjustable. The coefficient of static friction between the crate and the board is 0.30. Can you determine the angle at which the crate just begin to slip? Okay, I'll give you 5 minutes to consider this question by yourself. You can start now. Okay. Solutions to this problem. So in this problem, we have the following information. The static coefficient of static friction US is 0.30, right? And we want to find the angle theta. So the force of static friction on the crate can be as large as Fs equals mu s times Fn, where Fn is the normal force. First, we can draw the free body diagram of the crate, then calculate the normal force using the y components, then calculate the angle theta using the x components, and the fact that the object is in equilibrium. Therefore, we have the following relationship. The net force along the y-axis equals Fn minus Fg cosine theta. That gives us Fn equals Fg cosine theta. Okay, on the other hand, Fs equals mu s times Fn, which is mu s times Fg cosine theta. In the x-axis, we have the net force equals 0, which equals Fg times sine theta minus Fs, right? So considering these equations, we have Fg sine theta equals Fs. Then we have mu s equals sine theta over cosine theta, which is tangent theta. So mu s equals tangent theta. From this equation, we can find the value for theta, which is around 17 degrees. So the angle at which the crate just begins to slip is 17 degrees. Okay, any questions? All right, if no questions, let's have a look at another sample problem. So in this problem, we have a figure 6, which shows two blocks joined with a rope that runs over a pulley. The mass of M2 is 5 kilograms, and the incline is 35 degrees. The coefficient of static friction between M1 and the inclined plane is 0.25. So can you determine the largest mass for M1 such that both blocks remain at rest? Okay, I'll give you 5 minutes to consider this question, and after that, we'll have a look at the solution together. Right, have we finished? Okay, let's have a look at the solution together. So the given information is the mass of M2 is the mass of crate 2 is M2 equals 5 kilograms, theta equals 35 degrees, and mu s equals 0.25. And we want to find the mass of crate 1, right? So again, we can draw a free body diagram of this situation. As long as the blocks are at rest, the tension in the rope is equal to the force of gravity on M2. So Ft equals Fg2 equals M2g. Now we can consider M1. To remain at rest, net force must also be 0. First, use the y components to determine the normal force. Then use the x components to calculate M2. So we have the following relationship. The net force along the y-axis equals Fn minus Fg1 cosine theta. That gives us Fn equals Fg1 cosine theta. On the other hand, Fs equals mu s Fn, which equals mu s Fg1 cosine theta. And that equals mu s m1g cosine theta. Again, in the x-axis, we have the net force along the x direction equals Fg sine theta minus Fs minus Ft. And that gives us 0 equals mg sine theta minus mu s m1g cosine theta minus m2g. Then we can cancel the common factor g, right? And that gives us m1 times mu s cosine theta minus sine theta equals negative m2. Therefore, m1 equals negative m2 divided by the difference between mu s cosine theta minus sine theta. So we have all the numbers. Then put all the numbers in. We have m1 is approximately 14 kilograms. Therefore, we can make the final statement. The largest mass for m1 for the blocks to remain at rest should be around 14 kilograms. Okay, any questions? All right, if you don't have any questions, that's the end of C2L2. Remember to complete your homework on Google Classroom and submit them before the deadline, okay? I'll see you next time.